Hey, can you see my screen? Is it visible to everyone? Okay, great. Last class we have gone through this RNN, and again in this class also we'll continue that. So in the RNN, till now what we have seen, we have seen the forward pass, like that recurrence formula, like how to generate the state. So that formula we have seen. We have seen one example, character level language modeling, and that we have seen like we went through in a great detail. Then we came for the back propagation. So what I told you that like we can process, like one way is like we can process every word given in the paragraph or given in the input, and then like that for every word, let us assume that one word is considering as a or one word is considered as a one input, one sample for the input, like here this is one word, the second word, third word, and so on. So if we have like n number of words in the given paragraph, then and you are going to take the decision of that paragraph, then what you have to do, you just process every word here uh, in a sequential manner, and then you generate all the states, and suppose at every state you are also getting some output. Suppose in that problem you are getting output. Now if you are getting output, you can find the loss with respect with the help of ground truth, and at every state for the output you will be getting the loss, and then once you complete here, then you sum all the loss, and then you do the back propagation, just go back. So again, whatever path you have followed, you have to go in a similar manner. So you went for, you considering every state, you reach to this point. Now again you have to go back, then you have to follow the same path. Now the now if you do this, the problem was like the number of state could be very large. So if you have very large number of states, then there's problem, because then you have to store the information of every state, and then once you reach here, then again go back. Go back means like finding the gradient. So in the backward pass, you'll be finding the gradient. So again, computing the gradient, like you have it will it is having the complexity involved. Okay, so going back is also a space or time consuming process. So that is one thing. And other thing is like even in the forward pass, you have to store the information of every state. And if you have very large number of states, then the problem would be how to store those all the information. You could not be having that sufficient amount of memory where you can store these all the things. So this is the problem when you follow the just naive approach. Then the solution was, why not we should go with truncated back propagation through time. So instead of considering all words, what we'll do, we'll consider only this one chunk of words. Okay. We know that we have all the words in the paragraph, but we are not going to consider every word. What we'll do, we'll just divide that into multiple chunks, and at a time we'll just consider one chunk, one set of words. So this is like one set of words. So we consider these all the words in a sequential manner, and once I reach here, now I'll not go for the other words. Now what I'll do, since I got the loss at every state, now you just find the aggregated loss, and then go back, then find the gradient, and find the gradient and change the weight. Okay, so just go back with respect to every state. You find the gradient, and finally you will be reaching at this point, and then you just update your WHH, WXH. These three things you updated. You know that these three weights are shared across every state. So that's why you do the back propagation fully and reach here, and then you use those all the gradients, and then you update this and this. So this is called truncated back propagation through time. Okay, so this is for one set of words. Now in the similar manner, you go for the second set of words, which are like following words, which are coming after these words. So whatever words you have considered here, now after this, where these words are there. So now you go here. Okay. So now what you'll do? Now you know that your WXH, WHH, and WHY, WHY, these all the things has been changed. Why? Because you already have processed one chunk of words and it has changed this thing. Now for generating these all the states, you'll be using this new WXH, new WHH, and new WHY. All the updated Ws which you got from the first chunk. Okay. And then you'll be going to generate every state here with the help of input and the previous state. So here, like the state would be, the previous state would be coming from this point, and then you'll be following the similar manner what we have done in this case. And now you'll be reaching here, and again you have to go back. So again we'll find the gradient, okay? Now you'll be stopping at this point. You don't need to go further here because you already have done this part. Okay, let me just tell you, once you are done this part, now you can throw the all those gradient and all those information so that you will be having the space where you can now you can store all these new things. Okay, so that's the beauty, because every time you are just processing one chunk and doing the back propagation, and like whatever you are calculating there, just use it and then you just throw it out. Just remove all those things. And then once you go for the next chunk, again you do the similar stuff. Again you go back, you find the loss for every state, like output of every state, and then you once you reach here, then you go back and you have to stop at this point because this was the starting point for the second chunk. You don't go further, okay, because you already have covered this part. Okay, again you change the this WX and this WXH, WHH, and WHY, and then that is done for the second chunk. And in the similar manner, you can go for all the chunks. These are all the things we have seen in the last class. We also went through the some of the examples, some of the papers which have used this RNN for solving some of the problems. So I'll not go through again because you already have done this thing in the last class. These are all the examples that we have covered in the last class where people have used RNN, like visual question answering, then visual dialogue, conversation about images. Okay, now from here we'll start. Okay, so let's see, uh, let us rearrange or let us rewrite this RNN. If you just see the formula for the RNN, this is the formula for the RNN. So we have input xt, we have wxi, that is the fully connected layer which is getting multiplied with the input xt, and then this is the hidden state. It is also this is the old state, previous state, that is getting multiplied with the another fully connected layer, and then you are adding bias, applying 10h, getting new state. This is the formula that we have seen in the previous classes. Now let us rewrite this. Okay, so let's consider this WHH and WXH in a single matrix. So what we are doing, we just rewriting this equation. So now we'll consider WHH here, WHX here. So just make the one row vector. Okay. So where like the first part is your WHH and second part is your WHH. And then you make this ST minus XT, na? Just put these all things in a column matrix. So now we have here we have ST1 minus ST minus 1 and XT. Okay. So I've written the same thing. It's both are the same thing, just the different representation. Okay. So here also, if you do the multiplication, if you just do the multiplication, so this like row by column. So WHH will be multiplied with ST minus 1. That is your first term. And WHX will be multiplied with XT. Uh, that is your second term. So you are getting the same thing. I've just written in a different form. And then we have bias. Now, since I know that this is the W matrix, because here you have all the W's involved, WHH and WHX are involved. So why not consider this as a one big W? Just give the name for this whole matrix. Okay. So let us give this name as a W. So now this W, and then keep it as it is. So W ST minus 1 XT plus bias. And then finally you're applying 10H. So same thing, the same, like we started with this formula and then we have simplified it. Now this is like comparatively simple equation than this. Okay. Okay. So now let's draw it. Just see the visual, the pictorial representation. So what we have this type of visual representation. So we have W. In W, you have WHH and WHX in a it's making the row matrix. So you have WHS and WHX, and then you have to multiply this W with this column matrix. And in this column matrix, what we have? We have HT minus 1 and XT. So what we are doing here, we are stacking these two things in a column matrix. So ST minus 1 and XT. So this stack will give you this. And then at this point, this is the, like you are applying that fully connected. So your W is getting multiplied with this. And then after that, you are applying 10H. So whatever output you are getting from this, you apply 10H over that, and that will give you ST. So just I have written in the same thing uh, in a slightly different, we can say, uh, representation. Now let's see what will happen when we do the back propagation. So if you are going from here to here, let us take only this part. In the forward pass, you are giving ht minus 1, xt, w is getting multiplied there, then you are applying this 10h and then getting st. Now, when you go back, because you have to do the back propagation, when you go back from st to st minus, so what will happen? If you're going from st to s2 minus 1, that means what? You have to find the gradient of st with respect to st minus 1. So again, in this whole network, this RNN network, RNN layer, your whatever variables you have to find the gradient with those all the variables. And you can see here the variables are W and your state, because these all the things are getting changed. Your xt is fixed. So that's why you're going to find the gradient of the final thing with respect to state and with respect to W. But again, at the end, since you know that you have to only change the W, so at the end, just accumulate all those gradients, and then at the end, you should be having the gradient of final thing with respect to all W's, del W and del L by del W HY also. So this W is containing WHH and WXH, and this is containing W. So at the end, you have to find this, but going for finding this needs this part also. So you want to find this and this, but for calculating this, you also have to find the gradient of L with respect to state, or gradient of the output with respect to gradient of the output state with respect to the input state, because those are all also variables. So whatever variables you have, you find with respect to all those variables, and then at the end, maybe when you do the accumulate these all the things, then you at the end you just give focus on this and this part. But even calculating this part may be having, or it will involve this also, the state also. Okay, like the gradient of output state with respect to the input state. That will be also involved here while calculating these all the things. Okay. Now let's see, when you are finding the gradient of the output state with respect to input state, now what will happen? Suppose you are here at this point. This is one state, and you know that when you go back, your upstream gradient will flow from the right hand side, and at every state, at every point, you are also going to calculate the local gradient, and local gradient will be multiplied with the upstream gradient. That's like you're applying the chain rule. So at this point, suppose this is the local gradient. So local gradient, if I want to find local gradient W del st by del st minus 1, what would be the output? So just see this. This is the equation, and I want to find W del st by del st minus 1. Since I know that, again, let us ignore the 10h part. Again, 10h, there is a role of the 10h part, but just ignore 10h for some time. So just ignore this part for now. Now suppose you have this equation, Now, if you are finding W del HT by del HT minus 1, so this part is not involved. You will not get anything because here HT minus 1 is not there. Here also HT minus 1 is not there. Now, HT minus is only in this part. And since you know that this is the constant part, constant which is getting multiplied, like for this HT minus 1, since you are finding with respect to HT minus 1, then this part will be considered as a constant for this. Okay. So your gradient will be what? WHH. I'm just ignoring the 10H part, but there will be role of the 10H part also. Okay, but let's see. Even if you have not 10, if you are not considering 10H, then what will happen? So you got WHH, and this is from one state. You have to suppose you have n number of states. You know that you have to go from you'll be having n number of states because you have n number of words, n number of tokens. So if you have n number of words, n number of tokens, now you'll be having n number of states. And let us assume that let us consider one state. You know that in one state, if I find del h4 by del h3, it will give me WHH. It's not exact gradient, but I'm just giving the approximated gradient, okay, because I'm just ignoring the 10H part, but 10H part will also involve here. Okay. So even if not consider 10H part, I'll be getting this thing. This is the local gradient of this part. Even if I calculate the local gradient here, del H3 by del H2, that will be also WHH. Here also W del H2 by del H1, that is also WHH. So for every state, the local gradient with respect to state that we are getting is WHH. And you know that you have, suppose you started from here and you are going back. So every time your local gradient will be multiplied with the upstream gradient, because what is your goal? Your goal is to find WH4 by WH0. That's the goal. Goal is to find the gradient of the output, final output with respect to the initial input. That's the goal. Now at every state you are finding the local gradient, but when you are going back and when we are considering this, like every time when you are considering the upstream gradient, you are applying the chain rule, and what you are doing, what you are getting, your upstream is getting multiplied with the local. So for this part, suppose you got here you got del h4 by del h3, that is your WHH. But once I reach here at this point, then what I'm finding? I'm finding W del H4 by del H2. And when I have to find del H4 by del H2, I'll apply the chain rule. So del H4 by del H3 into del H3 by del H2. This is the thing that I have to do. This is your upstream gradient, and this is your local gradient. And what is your upstream gradient here in this case? You have WHH. And what is the local gradient? That is also WHH. So at this point, if I say, hey, what is the gradient of H4 with respect to H2, you'll say, hey, this is WHH into WHH. That is WHH power 2 square up. If I are here, and if I say, hey, what is the gradient of del H4 with respect to del H1? Again, the upstream is this for this, and one local gradient will be here, and that is what? WHH. So WHH into WHH into WHH, that will give you WHH to power 3. So every time your gradient is like the power of gradient is getting increased by 1. So if suppose if you have n number of state, and if I ask you what is del H n by del H0, then you'll be simply saying, hey, this will be approximately WHH power n. Just ignore the 10H part, but 10H part will be also there. That will also make some value. It will be also give you some gradient value, but let us ignore that part for now. Do you feel that this type of thing can give you some type of problem? So due to this, can we get, is it like, can we go in a very smooth manner, or will be having problem when I have this type of thing? The answer is yes, you may face problem, because you know that of this gradient of this Hn with respect to H0 is dependent, is having this value, that is WHH power n. Now suppose n is very very large, because many times we take n very large. If your n is very large and this WHH is having values very small, that could be one scenario. Just take scenario like what type of problems we can face here. So I want to find WHN by WH0, because this is being involved in my calculation, like when I'll be updating the W. So I want this thing. But the thing is, like, this is the gradient of this is equal to WHH to power n. And WHH is what? WHH is your fully connected layer. And this fully connected layer, suppose this fully connected layer is having the values very, very small. Suppose less than 1. In W, if every value is less than 1, and what you are doing, you are multiplying this W, this matrix n number of times, because we have power of n. If your value is less than 1, what will happen when we multiply this matrix with the same matrix? Because every time the matrix is same only. So suppose I multiply this WHH with WHH, like element wise multiplication twice. Now what will happen? Whatever value you had in this case, every value will be getting smaller. Why? Because your values are less than 1. So if I multiply 0.9 into 0.9, that will give you 0.81. And 0.81 is lesser than the 0.9. So when your values are less than 1, by doing the multiplication, every time your value, that the output value will be even smaller than the input values. And this is happening for the n number of times. And n could be very large number. So if it is happening for n number of times, what will happen? Maybe at the end, your values will approach to the zero. So close, it will approach to the zero. That means this gradient will approach to the zero. And why it is happening? Because this is dependent on the WHH. And in the WHH, if you have values less than 1, then there is problem. Like between 0 and 1, then there is problem. So in that case, you are getting gradient close to 0. And if your gradient close to 0, you know that there will be no update or very less update in the W matrix. Why? Because you are going to apply this SGD type of formula, and you know that your new W will be, this is dependent on the old W, old minus eta of your gradient. And if your gradient is close to 0, then this part will be close. This part will be close to 0. And if this part is close to 0, there will be no much change in this. Or it could be also the case that this part is approaching to the 0. In that case, there will be no change, because this A will be equal to this only, because this part will become 0. So what this means? That your model is not getting updated. And this is called vanishing gradient issue. We already have discussed in this thing when we were discussing the CNN part. So in this case also, in the case of RNN also, we could be having vanishing gradient issue. Now let's take another scenario. The another scenario is when we have very large value in WHH. So if you have very large value in the WHH, what will happen? If you have very large value and you are multiplying that value n number of times. So if a value is very large, and if you multiply that value n number of times, or you're finding the power of that, you're just putting the power n of that value, then what will happen? It will approach to the infinity, because multiplying large value with large value give you even larger value, and every time you are getting the larger value. So since your n is, if your n is very very large, that means you are multiplying that large value n number of times, and that n is very large, then what will happen? It will approach to the infinity. And if your gradient is approaching to the infinity, again, you will be having no update here because everything will be crashed because this part become infinity. If this becomes infinity, everything will be crashed. So what this problem is called? This is called exploding gradient because your gradient is exploding by the states. And why it is happening? Because you have a very large value inside this WHH or inside the W matrix. So we have two types of problem: exploding gradient problem, which occurs when we have very large value inside the W matrix, and we have vanishing gradient problem where it occurs when we have very small values in the W matrix. Now, how to sort it? How to solve it? Because we know that these are the problems, we have to solve it. So let us start with the first one, exploding gradient. So for exploding gradient, people have given like a lot of ideas in the past, and this is the idea that is being this is being used in general. And what this idea is? This idea is it's called gradient clipping. And what is say that scale gradient if its norm is too big. So what we are doing here? We are finding the norm of the gradient. Okay. So just find the square of this gradient, whatever gradient you have, find the square of this, and then you sum all the values. And that is called gradient norm. Okay. And then what we'll do? We'll compare this gradient norm with some threshold. And this threshold we are going to put. So suppose we put, hey, my threshold is maybe 8,000. That means whatever gradient I got, you know that your gradient is like, it's not one value, it's like it's matrix. Okay. So whatever values I got here, what I'll do, I'll just square all the values. I'll square all the values and then sum all the values. After squaring the values, we'll sum it. And what we'll do, we'll compare that sum values with some threshold. Okay. And what we have to check, like if this sum values is surpassing this or is coming more than this, then there is problem. Because the problem was why we were facing the problem? Because of having a very large value in this. And since I put this thing here, you should not go beyond this value. That means whatever sum, after squaring all the values, whatever sum we are getting, that should not go beyond this because this is my threshold. But if it is going beyond this threshold, that means we are in trouble. Okay. So for that, what we'll do? We'll yeah, so it's checking this condition. So if gradient norm greater than threshold, then what is happening here? It's it's mul it's multiplying this the gradient, whatever gradient you have, this. So it's like writing gradient equal to gradient into threshold divided by gradient norm. Okay. So whatever gradient you have, you change it because you know that since it the values of the gradient norm of this gradient is surpassing or is going beyond the threshold, that means we are in danger because if you are going beyond the threshold, it may lead to the exploding gradient because every time you will be multiplying this. So every time your local gradient will be multiplied with the upstream gradient, and that will again make the values even larger. So if we just face this problem, like once we identify it, then what we have to do? We have to somehow manage it. And for that, this is the formula that we apply. And what is this formula? This formula is very, very simple. Take the gradient and multiply with this value. And what is this value? This value is like threshold divided by gradient norm. So since I know that in your gradient norm is surpassing this threshold, and that's why you're facing problem. So why not divide this threshold by gradient norm? So if you divide your threshold by gradient norm, this value will be lesser than 1. Why? Because your gradient norm is larger than threshold. You have checked that condition. For lesser, there is no problem. If your gradient norm is less than threshold, will not do anything. But when your gradient norm is larger than or greater than threshold, then we are in the trouble. And for that case, we'll do this. So gradient multiply by this. Okay. So now you know that if you divide these two values, it will give you value less than 1. And you multiply this value less than 1 value with this gradient. So whatever gradient you have, you multiply every value of the gradient with the value which you got here. And this value is lesser than 1. It's like between 0 and 1. So what will happen? Due to this value will be getting smaller. Why? Because if you have 10 and if you multiply with 0.9, then that will give you 9. So if you have value and you are multiplying that value with the particular value which is having range between 0 to 1, this whole multiplication will make the first value even lesser. So initially we had 10 in that gradient. Now we multiplied with this 0.9, that will give you 9. So by doing this multiplication, your gradient is getting smaller, and that is the goal because you have to keep these all the values smaller. It's not that much smaller, but it should be in between. It should not go for like between 0 and 1 because you know that if it is going between 0 and 1, then you will be having vanishing gradient issue. So we don't want vanishing gradient problem. We also don't want exploding gradient problem. So whatever, so we should be like lying in between, so that things will be smooth. Okay, so whatever gradient you got, large gradient, that will be multiplied with the small values, and this will make this whole value. This will make these values smaller. And every time you will be doing it whenever you are identifying you are getting this condition. Okay, so this is called this is generally being used while using this RNN, and in practice people have used this multiple times in past, and if you just see a lot of papers they have used this thing wait and keep. Okay, but again this is also not the we can say very accurate formula. Why? Because here, since you are multiplying this value, so your actual gradient was this only. So you have the actual gradient, and then you are multiplying with this threshold divided by gradient norm. So now this part is putting noise inside this, because this is not whatever gradient you are getting here. That is new gradient. That is not the actual gradient. It's not coming from your it's not defined gradient what you got from this architecture or model. So that means you are putting some type of noises here because you are changing the gradient by this. Okay, so that is the problem. That is like, yeah, so that problem is getting introduced here. That noisy thing is getting introduced here. But again, since you have to, like, you are going to train it, so by the time model itself it will learn like, hey, I know that this part is the noisy part that is getting multiplied with this our actual gradient, and this is making this part also noisy. So I have to somehow manage it so that at the end, loss should be it should be low. So that model itself will learn it. So again, we are putting the noises, but somehow your model itself will learn it, and it will try to uh, reduce or minimize this type of issue, like the noisy issue. So we went for solving the exploding gradient problem because that's the big problem. But for solving that problem, we have to compromise with something. So this is like some type of compromise that we are doing here. Okay. So this I talked about the gradient clipping. Okay. So for this exploding gradient problem, we have gradient clipping. Now what about vanishing gradient issue? Now how to solve the vanishing gradient issue? So for exploding, we got the solution. At least this is a feasible solution. Like we can use it. I'm not saying that this is very highly accurate solution, but it can be used. Now let's see what we can do with the vanishing gradient. So for vanishing gradient, the solution is change the architecture. So for exploding, we got the solution vanishing this gradient clipping. But when we come to the vanishing gradient, then the solution is, hey, I'm not getting any direct solution. So why not we change the RNN architecture so that we'll minimize this vanishing gradient issue. So now change the architecture. So which architecture we should use it so that it will minimize the vanishing gradient. So LSTM came for the same purpose. So RNN says, hey, for the exploding gradient problem, I have the solution. I can use gradient clipping. But when you have vanishing gradient issue, I I cannot go with the same architecture. I'm feeling that I should change the architecture. Then what type of architecture I should take here so that it will minimize the vanishing gradient issue? And that idea came in the LSTM. The next topic is LSTM. So LSTM tries to give the solution for the vanishing gradient issue. So this was let us go for the LSTM. But before that, let's see the vanilla RNN also. So this is your vanilla RNN that we have seen before. So we have combined this WHH and WXH in a single matrix. That is your W. And then we have HT minus 1 and XT here. And then bias. And then finally you're applying 10H and then getting the state ST. Now this is your LST. Hey, I'll just pause for 5 minutes, and you guys can ask some question if you have on this RNN.
Three page back. So here, sir, actually, when you are saying the threshold, how this threshold will be calculated? Is it assumption
Yeah,
or
this is again one type of we can say hyperparameter. So you have to decide. So even you can play around this threshold and just see like which one is giving the best, or maybe some observation, because while doing this you might observe something. Just look the W matrix and just see when it is getting failed, what is the large value that making this whole thing in a exploding gradient issue. So that we need to, like, again, that's what I'm saying, like here you have to observe this states, and you
yes,
have
sir.
to. So that is one way, but that is very complex way, because every time you have to observe the state, see the values. So another way is like you just play around here. So just start with some threshold value, and then see like if that works or not. If it's not work, then change the value. So you can just play around this.
Okay, so you are saying one is with the iteration, each and every iteration you observe and put the value. The other one is that is wholesome assumption that let put me, then I change that to other to get the satisfactory answer.
Yes. So either you just see the whole states and then try
Yeah.
to find out like what could be the threshold value that I should put here, so that I'll be not facing this exploding gradient issue. The second is like, if since that is like, first one is complex, it's like hectic
Yeah.
a process. So why not we should go with easy process. So instead of observing the whole states, let's play around this threshold value. So just choose one value and then see like if we are facing this issue again increase the value, and like that we can further move.
Okay, sir. Okay, thank you.
Mm.
So in
Yeah.
case of RNN, there are multiple these dense layers, right? So as you were telling that there is a limitation, right? It will remember the certain layers, right? So when in case of backward propagation, suppose I have n number of dense layer, will it go to the last layer as well, like H0 to H4? And suppose I have H0 to H 1000. So these backward propagations will work similar in similar fashions, or is there any kind of limitation that when the dense layer will increase, keep on increasing, there'll be impact on the backward propagation as well?
No, this RNN is like, I've just talked about the one layer RNN. Okay, so here we have only one layer RNN, and in that RNN, these are the states that I'm talking here. So these are the different state. Like you started with H0, then H1, then H2. You are generating all the states in a sequential manner, just applying the recurrence formula that we have seen for the RNN. And in that recurrence formula, if you just recall, we have like WHH and WXH, and then WHY. These were the three fully connected layer. And these three fully connected three fully connected layers are is like shared across all those states. So if I'm here or here or here or here, everywhere we have the same W. same WHH, same WXS, same WHY. So it's like you're not using multiple different fully connected layers. Instead, you are just using only one fully connected layer. So it's not only one, but you have three tasks. Then you are just using three fully connected layer. It's the same three fully connected layer every time. Are you getting my point? Number of fully connected layers are only three, but you are using it again and again while generating the state.
So in terms of weight, we're feeding the same weight in each and every state, right? That's the only difference you're telling.
Yeah, your weights are same only. You are just reusing that weights again and again.
Mm-hmm. In that scenario, it's I understood now. Understood.
So you do not have different W's. So if in your W, if you're having very low values, so in every state you have the low values only in that W, because every state is having the same W.
I was thinking on other perspective, like I was just trying to recall the last class that RNN will remember in certain state, right? It cannot remember. There are certain limitations that it will remember, but it has limitations that at certain level it can remember the previous state. It cannot remember the entirely through 0802 to
Uh,
HN. There is a limitation in that cases, right?
that the
Yeah.
problem is that problem is vanishing gradient, because
Yes.
because so you are losing the information. So by the layer, since values are getting multiplied again and again, again and again, so like you're just losing some of the information. So again, even you cannot cannot preserve each and every information, because you have infinite amount of information. So even in if I, because what you are doing, you are just capturing the information from the words, from the input. Even if you are here at this point in the state, what you are like storing, you are just storing the information of this x1, because you do not have any information in the past. You are just storing the information of the x1 with the help of fully connected layer. You're just refining the x1 and then storing it. Again, if you are here at this point, what you are doing, you are just storing the information of x1, x2, and x1. Now x1, you know that x already you have processed the x1, and you got the state h1, and in the h1 you have the information of x1. Now with the help of h1 and x2, you are making h2, and now this h2 is storing the information of both h1 and x2. But in in h1 you could be having a lot of information. In x2 you will be having a lot of information. Now you're just combining this, merging these two information. So while merging, you will be losing some of the information, because you cannot store each and every information of x2 and h1 or x1. So you have to lose some of the information, and by the layer you are losing a lot of information. But goal is to just preserve the important information which can help me to do the particular job at the end. So this is the phenomena. But the problem is, like, when your W is having very small low values, every time is because every time it's getting multiplied. Okay, when you are finding H2, H3, then what you are doing? You are multiplying your W with H2 and X3. In W, what do we have? You have WXH and WHH. WXH is multiplied with this, and WHH is multiplied with this, and then you are summing it. Now, if W is having very low values, like values between 0 and 1, what will do? It will make this whole thing even like this whole thing even smaller. So every time the multiplication is giving, the output of the multiplication is having the smaller, lesser values compared to the input. And this is happening again and again. So maybe due to this, you may be approaching to the values where we'll be having all the values close to zero. So this can happen in the forward pass also. But I was just talking about the backward pass. So if you go in a backward pass, your gradient is dependent on, like, the gradient of the final state with respect to initial state is dependent on the WHH power n. And if WHH is having very low values between 0 and 1, and if you multiply this thing n times, then again values will approach to the 0. So that's why, like, this vanishing gradient is some problem of not remembering each and everything, not remembering all those crucial points when you have very large number of words, or when we'll be having a very large number of. You got the stuff or not?
Yeah, yeah. Yeah, got it.
So it's like long term. So if you have long long-term memory, that is the issue in this case. So it's not able to preserve the long-term relationship or long-term uh, information from the given chunk of word or from the given set of words. For the short term, it's fine. If you're going from here to here, there is no problem. But if your n is very large, then due to vanishing gradient problem, you'll be not able to update the W. And that's the problem because you'll be not able to train the model. Yeah, so let's go for solving it, the vanishing gradient issue. So the idea is use LSTM. So let's see LSTM and how it is helping us for capturing the long-term relationship. Okay, short term we were doing that was happening in the case of RNN also. But when we are going to very large number of uh, words, then the problem was occurring because the things were approaching to the zero. Okay, then how to capture that information? How to capture the information when we have long term? So for this, they have given this idea, and if you just see this like equation, it's like slightly complex compared to vanilla RNN. But let us relate it with the RNN. So in the case of RNN, we had one hidden state. Like this was like every time you were just generating one state, ST. Now in the case of LSTM, every time I'll be generating two things, two states. One is called cell state and one is called HT, like this. Okay, so ST, again, ST is there, but CT will be also there. Okay, and let's see like what is the goal of this. So the goal of CT is
Sir,
to
sir,
capture the,
can you repeat it again, sir? I just missed.
yeah, so what I'm saying here,
Yes, sir.
uh, yeah. So in the case of RNN, we had only HT. So every time we were just generating one state with the help of
Yes, sir.
past state and the current input. Now in
Right,
the
sir.
case of LSTM, instead of one state, now we have two states at every point. So one is your cell state and one is your hidden state, that is ST. Now the goal of the cell state is to capture the long-term relationship, which we were missing in the case of vanilla RNN. And the goal of this HT is to capture the short-term. That was also happening in the case of vanilla RNN.
Yeah. Okay, sir.
Okay. Now how we are getting it? Let's explore that part. So for getting this thing, we are doing these all the multiplication and summation, and then we'll see like what is the meaning of every component here. Okay, before this, let's see the initial formula or the initial components that we are going to calculate first, and then we'll go for calculating these two states. So the initial formula is okay. So we are having this W just like this vanilla RNN, similar to vanilla RNN. And that W is getting multiplied with HT minus 1 and XT, similar to this, adding bias, similar to this. But we have here four different things. Okay. So we applied this W over this added bias, and then we applied these four activation functions. So first three are same, sigmoid, 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 and then we are applying 10. Please, okay. So we are applying sigma, 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 and 10H. And first three are giving you IT, FT, OT. And last one is giving you G. Okay. Let me just relate with this with the RNN. So if you relate this thing with RNN, if I say, hey, what is this part? This is giving you GT. You can say, this is looking like similar to vanilla RNN. Here also we are applying WHT minus 1, the same thing, then adding bias and then applying 10H and getting this ST. So last term is similar to the vanilla RNN. But apart from this last term, last component, we have three more components here. That is IT, FT, and OT. And there's meaning of these all the things, these all the components. Okay. So let's explore one by one. Let's see one by one. So these four things call as a gate in the case of LSTM. This first one is called input gate. This second term is called forget gate. This third OT is called output gate. And last term is called gate to gate. So they have not found a very suitable name for this. So that's why they have given gate to gate. Okay. But this gate to gate is storing the new information, or we can say the information similar to the RNN what we are getting here, because GT is like a similar formula. Now let us understand like what is the purpose of every gate. But before that, let's see what would be the size of the W matrix. So in the case of your RNN, if you're multiplying W, like what you are doing, you are W HT minus, oh, sorry, X. So you had like W, and then you were multiplying WX and then HT minus 1. Or maybe it could be vice versa also. It's no issue. Because you know that if you're changing the order here, you have to change the order here. Because in the W, you have two things, WXH and WHH. These two terms are there. So we are multiplying these two things, and then you were applying 10H over that. That was the thing. Plus bias also. And then we are applying 10H over that. And you are getting the HT, the new state. Now, what would be the size of this? Let us assume that the size of this X and H is H only. Okay. So xt, the size of this vector, because you know that xt is vector, st is also vector, st minus 1 is also vector. So let us take the size of xt vector as a h, and size of the ht minus 1 vector is also h. So we are assuming that the size of the hidden state, the hidden state as well as the input is same. Now, what would be the, hey, please mute yourself. So here, if I ask you, hey, what would be the dimension of this? You can say in this xt is having h1 h dimension, and st is having st minus 1 is having h dimension. Then in totality, since you have put in a like in a single column, then it's having dimension 2h into 1. Okay. Similarly, if I ask you what is the dimension of BH, okay, before going to BH, first, what is the dimension of W? W is getting multiplied with 2H. The last dimension would be 2H. And again, you are going to generate the state with the help of this. So you know that the size of the state is H. Okay, so W will be having the dimension H into 2H, and which is getting multiplied with your input, this xt and xt minus 1, that is 2H into 1. And this multiplication will give you H into one dimensional vector. And again, your bias will be also having the same dimension, H into 1. And then you add these two terms, apply the 10H, and you will get HT. And HT you will be having H into one dimensional vector. This is the thing that we already have seen before. Now let's see the LSTM part. So in the LSTM part, what I'm saying you, hey, I want four things. I want four components. One component is not sufficient for me. And every component should be having the same dimension. And it should be having the same dimension as we have the state dimension in the RNN. So RNN was having the H1 into 1. So I want the same dimension, but for every component. And how many components I'm going to calculate here? I'm going to calculate four components: input gate, forget gate, output gate, and gate to gate. So for every component, I want H values. So in totality, if I see, I want 4H value. Okay. So if I want 4H value, what would be the size of the W matrix? The size of this matrix is fixed, because here HT, you know that this is H. XT, you know that this is H. So we have 2H into 1. Now, what will be the dimension of W here? So the dimension of the W would be 4H into 2H, because I want four different things, four different gates, and every gate should be having the dimension H. So this is your fully connected layer that you have here. And this is getting multiplied with your input, and it will give you vector is having 4H. The dimension of the vector is 4H. But what is the next goal? Next goal is You separate out every h value. So initial first h value, just take it and apply sigmoid. Then the next h value, again take it, apply the sigmoid. The next h value, take it, apply the sigmoid. Next h value, take it, apply the 10h. And now whatever you are getting, that will call as a first term will be called as a input gate, second term will be called as a forget gate, third term will be called as a output gate, and fourth term will be called as a gate to gate or the new information. So last term is giving you the new information because the similar to the RNN. In the RNN, you were getting the new information in the ST. ST was like aggregating the information, all the past information and the current input, and that was the new information that we're getting. So last term is giving you the new information, the G term, and these three terms are like gate. This is also gate, but these three are having some different role. It's having different role. So now you're getting this. Now let's see what every gate is doing. So what gates are doing? Now let's understand the meaning of every gate. After getting this, getting these all the states, now you are going to calculate first cell state, and then you have your hidden state, that ST. So for getting the cell state, you are using this is the first term and this is the second term. And you are doing the element wise multiplication here. So taking the FT and doing the this element wise multiplication with CT minus 1, and this is your first term. And in the second term, you are taking the IT, doing the element wise multiplication with GT, and whatever you're getting here, this is the second term, and then you add these two terms, that will give you CT. Now, what is happening in the first term? In the first term, your CT minus 1 is the past state information. And this CT minus 1 is storing the long term information. And now, what you are doing, you are filtering the information from this previous state with the help of FT. And the goal of FT is to forget some of the information from this. So it will say, hey, I don't want every information to be carried forward. Because I know that in the CT minus 1, since it is considering all the information from previous inputs, now in this CT minus 1, we could be having some noisy information. Then why should we proceed those information? So forget gate is, it will control this CT minus 1. So it will take the CT minus 1 from the previous state, and then it will apply the FT. And FT is your gate. Now it will decide like which value I should carry forward or which value I should erase or how much I should erase. And that you are controlling with this FT. And how FT is coming? FT is coming, whatever value you are getting here, then you are applying the sigmoid. And once you apply the sigmoid, you know that every value in that vector, in this I vector, or sorry, in this F vector, because this F is also coming from sigmoid, I is also coming from sigmoid. So in F vector, whatever values I'm getting, every value will be between the range of every value between 0 and 1. Okay, so if I just plot the FT vector, so it would be having values 0, maybe 0.1, and like that, it would be maximum value could be 1. And this is your gate. And now this gate, this forget gate is getting multiplied with CT minus 1. And CT minus 1 is also one vector because you know that every state is also vector. And then you are doing element by multiplication between these two. Okay. So in the cell state, you in the CT minus 1, you have the information of the past. You have all those information here. And the forget gate is deciding like which information I should forget. I should erase. I don't want to preserve this information. So if suppose it is having a lot of information, and suppose your forget wants to erase this first one information because it feels that hey, it is not required. So what will do? It will just put 0 here. Suppose it wants to preserve this information fully, then it will take 1 here. So that whatever value here, it will carry forward as it is. Sometimes this is not hard gate. So it's like soft get. So it can also give percentage. So sometimes you can also get 0.5. That means 50% of of this value I want to preserve and 50% I want to forget. So in that way, this gate is helping you to filter out information from the. So it will erase all those information which are not very crucial for taking some decision. And this is happening on the long term, like on the state which is capturing the long term relationship. So first part is just taking the information, taking the ct minus one from the previous state, and then erasing some of the information, and then you are getting the new vector here in the first part. Now let's see the second part. In the second part, you have IT and GT. Now in the GT, if you just see the GT part, you know that GT part is similar to the RNN. So in the GT part, you have the information, you have the new information because it has seen state, the current state, past short-term state. I'm not, it's like just considering the short-term state and the input, current input. So now in this GT, we have the new information. It's like containing the all those information, how much, like what should be the information in that. So get is like how much to write to the cell. Because here the range is 10h. Here the activation function is 10h. And 10h is like will give you values between -1 to 1. So it's like normalized value. So again, you are working on the normalized value. So we have all the values between -1 to 1. Okay, between -1 and 1. Okay. So in GT, it's like what we should write there, how much we should write in in every point of that cell, in every cell of that. So GT already has done that. Okay. So while calculating GT, you got like what should be the new information in that. Okay. So it's just giving you new information. You're getting the new information, how much to write to the cell, what should we write in every part of the cell, in every part of the vector, and that you got from the get to get G. Now the thing is, G is coming from HT minus one previous state. It's also having the XT. These two informations have been incorporated in GT. Now it could be the case like all those informations are not crucial. So whatever you are getting as a GT, now again you will apply one gate over that, and that is your input gate. An input gate will control or it will filter out the information from the GT. So whether to write or this is just similar to the first part only, but in this case, the goal is to keep the information. In this case, the goal was to erase the information. So here the goal was, hey, the information which are not required, you erase it. Here the goal is, hey, just see which are the information which are required, just keep it. So the procedure is more or less similar, but goal is slightly different. So here you have to erase the information from the past which are not required. Here you have to keep the information from the new information that you got, and that is being controlled by your IT. And again, if you see IT, this IT is also coming after applying sigmoid. So sigmoid, again, you know that in IT, your values would be between 0 and 1. So all the values would be 0, 1, 1. And it is getting multiplied with GT. And GT is having the values between -1 and 1. So it's like how much to write to the cell. So whatever we have written in the cell, now you have to see like which part I want to keep as it is. So you have filtered out the input, filter out the new information, you have filtered out the past information. So this is like filtering out the past information, past state information, and filtering out the new information. And then you are adding these two terms. And that's giving you CT. That is your cell state. Okay. Now this cell state is for long term. It's storing the long term information, long term relationship that is being captured there. But you know that you have the short term state also that we have seen in the case of RNN. So from this long term, or cell state. Now let's refine or let's extract the hidden state or short-term information. So for that, what we do, what they have done, they applied 10H over this CT. So whatever CT you got here, after doing these all the things, then apply 10H over that, like just for putting the nonlinearity. And then they have applied another gate over that, and that is called output. So it will say, hey, I got CT, but I don't want to show every information from the CT for the HT. I only want to show only this much information from the CT, and that is being controlled by your OT, and that is output gate. And if you just see output gate, again, it is having values between 0 to 1. So it will say, hey, I only want, we have this much information, but this is coming from, it's like, it's having all those long-term relationship based information. So since CT is already catching that, then I'll just consider ST for short term. And for short term, I don't want everything from the long term relationship. In the short term, I just want the short term relationship. And that is being controlled by your OT. So OT will just decide like how much to reveal from this state, from this cell state. So applying 10s CT and then do the element wise multiplication, and that will give you HT. This is your LSTM. Now we need to see how LSTM is helping you to come out from this vanishing gradient issue. So we have like this is the LSTM. Only this part is LSTM. So this equation is for the LSTM. That's all. Now how it is helping us for coming out from the vanishing gradient issue. So for that, first we need to make the just uh, make this like show it pictorially. So make it as a diagram, whatever equation we have seen. So let's see, like just putting everything in a diagram in a pictorial manner. We have to calculate IT, FT, OT, GT. So you calculate F, I, G, and O. These all the four component. And for calculating this thing, what we need? First, we need to do this. So we have W here. This is the fully connected layer. And then we'll take the HT minus 1 and XT. We'll stack these two things. So that will be having XT minus followed by XT. So HT minus 1, XT. So this stack part will give you this HT minus 1 and XT. And then W is getting multiplied here. And let us ignore the bias part. Bias part will be also there, but just ignore it. And also let us ignore this activation function. This is also there. This is the main part. Okay. So after doing it, you'll get F, I, G, O. Now these are all the four terms by applying different activation function. Now we have to find the CT minus 1, CT. So CT, you have to do this thing. So let's do that. So let us do this thing first here. So I, G, IT into GT, do the element multiplication here. So I into G, that will give you this second part. For the first part, you need CT minus 1 from the previous state. So CT minus 1 from the previous state. And then F from here, from this state. So F from here, this F, and F is getting here. Then element by multiplication. And then this is the first term. And then you have to add these two terms that we have seen there. So add the first term and second term. So that we are doing here. And that will give you CT. So you got the CT. So just I'm showing in a pictorial manner. That's all. Now over CT you apply 10H and then you do the element wise multiplication with output gate. Output gate here. This and that will give you H2. Now we got this. Okay, and now we got the pictorial view of this equation, because we have to somehow realize like how it is helping me for solving the vanishing gradient issue. Because that's why we shifted to the LSTM because of that. Otherwise, RNN was also doing fine. But the thing was, it was struggling with vanishing gradient issue. And why it was happening? Because it was when it was going to capture the long-term relationship, then it was getting failed due to that vanishing gradient issue. Now the goal of the LSTM is to come out from that, and it says that, hey, I have given this equation, and now this equation is helping you to come out from that situation. But again, we have to realize it, how it is helping us. So for the realization, this diagram is must, because this diagram will give you the idea how it is happening. Now let's go back. Let's do the back propagation. Hey, I'll take 5 to 10 minutes more to because I have to complete this part. Is it fine to everyone, or should I stop here? Okay, great. So now we have to realize it, how it is helping you to come out from the vanishing gradient issue. Now we see here, we have two things. We have two states. In the case of RNN, we have only one state, like only one type of state. Here we have two type of states, ST and CT. Now this, let us ignore the ST part because we know that if you're going to find W del ST by del ST minus 1, then since this is coming from by doing this W multiplication here, then anyway, like we have, there will be involvement of W. And that is the problem because that W is getting involved and it's every time it's getting multiplied and we are getting W to power n. And this was the problem of this vanishing gradient issue. So this is one path which you can follow. And that we already have seen in the case of RNN because this path is similar to the RNN. Let's follow the other path, which is your bypass route. And that is happening due to through this cell state. Okay, so either like you'll also go follow this path, you'll also follow this path. And then at the end, you'll combine these two, like you'll just aggregate the gradients. So suppose you are starting from here, going here, suppose this is one branch, this is one branch, this is one branch, and then you are calculating something here. If you're going back, and if you got some gradient here for this branch, and if you got some gradient here for this branch, now at this point you will just sum these two gradients. You'll just aggregate these two gradients, and that will be the final gradient of this with respect to this input. This we already have seen in the like when I was discussing the this back propagation part. Okay, so just follow the first path. So in this path, if I want to go from CT to CT minus 1, what will happen? Let's see. So I started from CT and I want to go to the CT minus 1. That means I want to calculate del CT by del CT minus 1. I'm just writing del, but it's like gradient. Okay, it's a gradient. Okay, so gradient of CT with respect to CT minus 1. Now let's go back. What will happen? So again, this is not your final state. CT is not the final state. You could be having a lot of different state this side. You could be having maybe you may be going to the N state. So from this side, you will be getting upstream gradient at this point. Suppose you are I'm considering this part. So you'll be having some upstream gradient which is coming from the right hand side. So suppose you got some upstream gradient at this point, which is coming from the right hand side because you have all the different state on the right hand side. So you got some gradient here. It should go back. Now at this point, this is your CP. And yeah, so from this point, it will go as it is because here at this point, nothing is happening. It will go as it is to back. Now at this point, we have addition. And whenever you have addition, what happens? If I write A plus B, this is your, like this addition is your local function now. So you have the local function addition. So whenever you have local function addition, what happens? What happens with the upstream gradient? Suppose if I'm writing C equal to A plus B, what is the local gradient here? Del C by del A, 1. Del C by del B, 1. So your whenever you have addition, the local gradient will be 1 for every variable. And you know that your local gradient will be multiplied with the upstream gradient. And since your local gradient is 1, so that means whatever upstream gradient you are getting, this will be given as it is to all those variables. So it will be like distributed the same value because local is 1 only. Getting my point? Okay. So now whatever gradient you got here, whatever gradient, maybe G you got here, there is no change there because G will be given to this, G will be given to this. Oh, I should not take G because G is already we have used here. I should take maybe Z. Suppose you got Z from here, Z from here, and you have now this is addition. I'm just ignoring some of the parts, but I'm just giving focus on the more like most important part. Okay, so there will be all different operations also while doing these all the things, but these are like most important of function which can change these all the stuff, which can create more effect on the result. So whatever Z you are getting here, that due to addition, it will go as it is to both the side because addition will local gradient will not change. Like local gradient will be 1 in for every variable, and upstream will be just multiply with the local gradient, and it will remain as it is. Now this part is done. Addition is done. Addition there is now it has not changed the gradient. So whatever gradient you got as a upstream, it will be given as it is. Now let's come to this part. The second part is like now in this part we have multiplication, and this is element wise multiplication. Now whenever you have multiplication, if I'm writing p equal to x into y, now what is the local gradient with every variable? So if I write del p by del x, this will be y, and del p by del y, this will be x. So while calculating the gradient, your value is getting exchanged. So with respect to x, you will be getting y. With respect to y, you will be getting x. So now here we have multiplication, and we have to go back in this path. Okay. So it means I have to find this local gradient. Suppose this is the output, this is the out that I'm getting. Just considering the local. So del out by del CT, that is my focus. Now del out by del CT will be equal to F because your operation is what? F into CT minus 1. And you are finding the gradient with respect to CT minus 1. This part will be coming out. Just like here. With respect to X, Y will come. With respect to Y, X will come. So with respect to CT minus 1, F will come. With respect to F, CT minus 1 will come. But our goal is to find with respect to CT. Again, you also finding with respect to F. But that part is not getting fully involved here. So whichever part is involved here to reach CT minus 1, I'm just considering all those parts. So now this is F that you got. And then this F is your local, and it should be multiplied with Z because Z is the upstream that you got. Now, let us assume that in F, most of the values are 1. In F, if the most of the values are 1, because F is the forget get, and values between 0 to 1, and let us assume that most of the values are 1, then what will happen? The output would be very close to Z. So that means if I find del CT by del CT minus 1, if I just remove some of the things. So if I find del CT by del CT minus 1, this is equivalent to F into Z. And what I'm assuming, my assumption is that F is having most of the values 1. If that is the case, then this should be equal, like is equivalent to very close to Z only. So this is very ideal scenario. I'm assuming F is having, that means I don't want to forget most of the values. Okay, if this is the case, then what happened? Whatever we had Z here at the CT, we got the same Z or similar Z at CT minus 1 also. while calculating the gradient. So it's not changing the z, it's not changing the gradient. Whatever gradient we are getting whatever gradient we have at this point, we are getting almost similar gradient at this point. And why it is happening? Because just going here, we have one addition, and addition, you know that addition will not change anything. Its local gradient will be one. So whatever we have upstream, it will just forward it as it is. Only multiplication can change. So multiplication, local gradient will be like exchanged. So you have f, and our assumption is that f is having all the values close to 1. That means this f is also close to 1. And if it is close to 1, then that means z will be also not changed much. So we are getting almost similar of a gradient at this point what we have here. This we wanted to get. We wanted to get z. We wanted to get gradient. We wanted to get some good values in the gradient. Because in the case of RNN, we were following this path where W was involved. And W was the culprit because it was changing the gradient drastically because it's getting every time W was getting multiplied and W to power n approaches to infinity. And if W is having values close to zero, then every value will approach to the zero. And that was the problem. And due to that, we were not getting gradient. We were getting gradient close to zero. But now we have one another path, that is your CT. And CT is more smooth path. This can be seen as a bypass route. If you want to go to Patna, you want to go to maybe yes Patna. So one route is like you just follow the city road, and one route is like bypass route. So if you go through city, a lot of traffic will be there, and there's problem there. But if you follow the bypass route, you will be reaching fast. So this is the bypass route, which makes the gradient or which makes this process okay. And at least you are getting some gradient at this point. So suppose in this from this path, from the second path, because you have the two paths. One is this path, one is also this path. Suppose from this path you are getting gradient close to zero because here W is getting involved. But from this path, since your W is not getting involved, so in this path you will be getting some values. Suppose maybe P values or this Z values. So now if you overall sum these two, aggregate these two gradients, you will be having some gradients here. So now due to this, you might not be facing the vanishing gradient issue. Because every time you have one path by which your gradient is flowing very fast. Here, it might change the gradient drastically, but from here, there is less chance to change in the gradient drastically. Okay, so this was the idea of the LSTM. So this is the bypass route. And this you can see as a residual connection also. This just you can relate this thing with the residual model, a residual layer which we have seen in the case of residual network. So there also we have like two routes. One was you can just recall it. So we have the function here, and one was direct route. And when we were going back, then you will be following this route, and you will be also following this route. So from this route, whatever gradient we had here, that is going as it is. But from this route, you have all those operations which are happening here. So this may change the gradient, or by changing this multiple times, this may approach to the zero. This part is not changing the gradient. And from this part, at least from this part, you'll be getting good gradients. And then if you sum it, because at this point you aggregate these two gradients, and that will give you some good gradients. It will give you like good gradients, which may stop you to like to go for this vanishing gradient issue. So this was the solution of that. So this is also similar to the residual type of network. Here also we are going, one is CT that is going directly, but this ST is following it's going through all those functions. But CT is going directly. So again, this idea also they have this very similar to the residual idea, residual network idea, that layer idea. But here again, they have incorporated it with respect to RNN. There they have incorporated with respect to CNN. That's the difference. Now, everything is good, looking good. But in this case, LSTM, let us just see one point. When I was saying, hey, I'm getting this, the final gradient of this del CT by del CT minus 1 equal to F into Z. Z is like upstream gradient. Now, this is dependent on the F. We have considered the ideal case where we assume that most of the values of the F are close to 1. But in reality, you could be having, there is no guarantee that every time you'll be having most of the values close to 1. Suppose if your model wants to erase a lot of information from the past cell state, then it may be having a lot of values close to 0. If that is happening, then there is problem. Then it will make the value of Z, most of the values of Z close to 0. And then again, we'll be having the similar type of problem. So LSTM is not the fully, it's like well proved, or it has not solved this problem in a like, it's not in a full manner. Like, it's not fully solved problem. But again, it has given the idea that, hey, if you use this idea, you might be having better training compared to RNN. So it will somehow sort out that issue, but not fully, because you know that this dependent on the F. So if F is very good, then everything will be good. But if F is not very good, then things will be weird. Like, it may again, you can again struggle with vanishing gradient issue. So this is the idea. You can use it, and that's why LSTM came and given this idea. But again, it's not full guarantee. Okay, so I just talked this thing, uninterrupted gradient flow. This is similar to the ResNet that I already have told you. It's like bypass route. Mm, From the top, it's going. If you just relate the formula, it's also very just you can also relate the formula, and it's very similar to the residual like curve structure. Only slight modification is there. So it's just like your CT minus 1. In this FT, this is the like, this part is the, you can see that this is very close to the residual structure also, a residual formula also. So in the case of residual formula, what we have, like, if you want to get Y, so it was like, maybe not Y, should not write Y. If you want to get XT, so it was like equal to XT minus 1 plus F of XT minus 1. This was the formula that we have seen. So like this, your XT minus is giving as an input, and then this is your function, and you are getting output here. And one XT minus is going directly. So here, like, addition is happening. So XT minus 1 plus F of XT minus 1, and then summing this, and that is your XT. This was the formula of the residual. Now you can also relate, this is also very close to that. So this first part is this function which is happening. This can be seen as a F, and this part can be seen as a your XT minus 1. The only thing is, like, here FT is also involved. So CT minus 1 is like previous state, but that is also getting multiplied. So FT is the main, we can say, that's the difference. And FT is also playing the major role. So if your FT is very good, then you are very good. Then if FT is very good, that means you are very close to the residual block. But if FT is bad FT, like it's having values, a lot of values close to 0, then there's problem. Then you may face that missing gradient issue. Okay, so with that, we have completed this LSTM part. Now, some of the things are left. Uh, maybe in the next lecture, I'll talk it. So I'll stop here. Okay. Sorry, I have taken extra time. Okay. Thank you.